Welcome back. So, we are looking at the problem cases in Prolog where your program could get into an infinite loop essentially, especially when it comes to recursion essentially. So, we started by looking at this definition of above. We looked at 3 definitions of above. In the first definition, you are looking at, you are saying x is above z if x is on y and y is above z. So, somewhere of course, you will search further. So, obviously, if you use the same recursive definition, then this will lead to a second query which says x is above y, y is above y 1 and that y 1 is above z essentially. So, you will gradually grow from the top only looking at those objects on which this one of the objects is there. Whereas, in the second query, we have this possibilities of all those y's, we want to look for all the y's which can be below x. So, let us see what happens there. Remember, our knowledge base is simple. We have A, B, C. A is on B, B is on C. If we say above A, B, whether it is true or not, the first version of our predicate which is called above will say true and then it will say I cannot show anything else, because the recursive clause will stop there essentially. It will not be able to. You see, if you were to use a second definition, it will also give you the answer as true, as I had said that you should work it out that it is indeed the case. But trying to look for another answer, because it is left recursive, it will try to go into, it will get caught in an infinite loop. The same thing will happen with the third definition, and the problem with that is, as we saw earlier, that the first clause is a recursive clause which is a left recursive program, and they will go looking for answers and eventually your machine will give you a stack overflow problem. Now, if you look at this answers A, B, C, if you look at these blocks A, B, C and you ask a general query, is something above something else, then you can see that there are 3 answers to this, that A is above B, B is above C and A is above C. So, ideally, if you were to ask this general query which is with variables, it should generate all the 3 answers. But we have already seen that there will be a stack overflow here. So, Prolog allows you to shift into a data driven mode and says that create a table of whatever you know. So, you have seen that A is above B, B is above C and so on, and then work with that table essentially. This process is called tabling. We will not go into too much detail, but I just wanted to highlight the fact that modern Prolog will allow you to prevent infinite recursion on left recursive rules essentially, and you can do that by this process of tabling. What happens if you do that? Then all 3 versions of the definitions will give you the same 3 sets of answers. They will end a little bit differently. The first version would say that there are no more answers, the other 2 will terminate after giving you the 3 answers, because they are the only answers which occur in the table essentially. So, this is just to let you know that there is a way of avoiding infinite recursion in situations where you must use this table feature. So, here is another example. You are creating a table for the sibling predicate. The sibling predicate is defined here on the right hand side. There are two facts given to you. Eva is the sister of Ada and Dan is the brother of Ada. This is given to you. And the query that we are going to ask is that are there two siblings in our database, and our rules for defining siblings are as follows. The first rule says that if you are a sister, then you are a sibling. The second rule says if you are a brother, then you are a sibling. The third rule says that if x is a sibling of y, then y is a sibling of x. This is like that married thing that I had mentioned earlier essentially. And we have another rule which says, which is a transitive rule. It says that if x is a sibling of y and y is a sibling of z and z is not the same as x, then x is a sibling of z essentially. So, if there are three individuals, you can, and you know just this information, then you can, what is given here, then you can conclude that who is a sibling of y. So, ideally the answers that you would expect is that yes, Ada is a sibling of Eva, Ada is a sibling of Dan, that is given to us in the database itself, but also that Eva is a sibling of Ada and Eva is a sibling of Dan, and that Dan is a sibling of Ada and Dan is a sibling of Eva. So, you can see that this is the same this, but because of this call we have generated two answers, two separate answers. But because of the fact that we have used the table feature here, we have stopped with those two answers and we have not gone into an infinite loop, repeating that. So, we are not going into an infinite loop in this clause, that if x is a sibling of y, y is a sibling of x, and therefore, x is a sibling of y and therefore, y is a sibling of x. We are not going into that cycle, and that this table feature allows us to do. So, this is known as SLG resolution, tabled execution. It memoizes, that means it remembers what are the answers that it has found so far. It is a form of data driven computation, and benefits of memoization are that it avoids predicate re-evaluation, improves performance. If you have evaluated this predicate once, it does not evaluate it again essentially. It avoids infinite recursion of left recursive rules. It avoids infinite recursion due to loops in data. It removes duplicate answers. Okay. So, for further information, you should look at this documentation given on the SWI Prolog site. So, we have been talking about goal ordering, that goal ordering is important. Here is our favorite statement. We started the course with all men are mortal. X is mortal if X is a man, and we have some data. Alexander, Aristotle, Plato, Socrates, these are men, and Alexander is a king and Zeus is a king essentially. So, if we ask a query, is there somebody who is mortal? Our program will give us all the four answers, as you can see here. If you ask, is there someone who is a king? Again, it will give you two answers. If you ask a query that is there someone who is mortal and who is also a king. So, we have Alexander is mortal, Alexander is king. Then irrespective of the order in which you give this query, mortal first and king afterwards, Prolog will do your job for you and tell you that yes, Alexander is such a person, and it will also tell you that there is no other such person. So far we have not spoken about negation. What if you wanted to say, is there somebody who is a mortal and who is not a king? You can see in the example here that there are three such persons: Aristotle, Plato and Socrates. They are mortal and who are not kings. How can we do that in Prolog? The key part is who is not a king. What is even more difficult, as we will see shortly, is if we reverse the order. If we ask, is there somebody who is not a king, but who is a mortal, then we can run into problems. That is a problem that we are going to see, which comes with the way Prolog thinks about negation. So, I have already said that Prolog uses negation by failure. If it cannot show that something is true, then it will say that it is false. So, now let us put the negation in our queries. Can we ask this question, that somebody who is not a king and who is mortal? We will do that in the next session, I think.